Hello, my name's Nick. I'm from EPCC at the University of Edinburgh. And as part of the Accelerat European Centre of Excellence, we're looking at a whole load of engineering codes and how we can adapt these for exascale. And one of the big questions is the hardware technology that we will have in such future supercomputers. And I think FPGAs really are a prime candidate here. But something we see a lot of for these different codes is there's really a big performance difference between the first version of the code running on the FPGA and then the final version that's optimized for the actual technology. Now, this might not be a surprise to you in the audience, but using things like high-level synthesis, C, C++, these languages are based on von Neumann foundations. And really then moving the code to a dataflow algorithm is often not that obvious. It requires lots of expertise, and especially with the long build times for the FPGA, can take a long time to get this optimized code. I mean, with this example here, for instance, there's something like a 4,000 times difference in performance between the first version and the optimized version. And what we often end up with is something like this thing on the right, where in our minds as the programmers, we've got a data flow machine where we've got different filters running concurrently, streaming data between them, and the trick being keeping all these different things running actively concurrently on the FPGA. So I think there's a big argument to make to say, hey, why don't we present the programmer with abstractions so they can implement this like so, first time, every time, so their code is fast by construction. And I've talked about these data flow machines. Obviously, this was an area of research that was very, very topical back in the 1970s and 1980s. And at that point, quite a few languages and solutions for programming these data flow machines grew up. So I think, now we are getting more and more use out of FPGAs. Lots of people, completely agree that data flow is the way you need to view these things. It makes quite a lot of sense to look back into history at some of the languages that were developed back at that time for programming these general purpose data flow machines. And what can we learn from them, and how can we apply them to our modern FPGA technologies? And arguably one of the most prominent languages back in the day for programming these machines was Lucent. So this is a declarative data flow language where the time dimension was a first-class concern. So looking at the progression of data over time explicitly. And this was rather popular and quite successful. So what we've looked at doing is developing a follow-on from Lucent, but targeted towards FPGAs. And we call this Lucent. Now, crucially, we are looking at doing something subtly different to Lucent, because you can imagine Lucent was providing the programmer with abstractions for programming these fixed general purpose data flow machines. What we're doing in Lucent is we're aiming to provide the programmer with abstractions for designing their own application specific data flow machines, which then the FPGA is configured to look like this data flow machine. It will run, and then obviously it can be reconfigured to look like any other application specific data flow machine after that. We've also modernized the language and things like explicit typing for the FPGA as well. But a lot of the foundations are built on what they were looking at a few decades ago. So for instance, with this example on the left, what we're declaring here is the result from the kernel is A plus B, which are inputs. And crucially, data's never at rest here. It's streaming in continually, and from one time quanta to the next, we're then progressing and streaming out lots of values, with EOD being the thing that terminates the run. In the middle, slightly more complicated, we're streaming in lots and lots and lots of values here with A, and we're checking each one of them. If it's less than 10, then we emit 1, followed by in the next time quanta 2, otherwise 0. And things like followed by, which come from Lucent, this is how we can then interact with these different time quanta. For instance, this thing at the bottom is just an incremental counter. We're declaring this thing down here, which increments up each time quanta. And you can map this code diagrammatically to my view of the data flow machine. And then on the right, more complicated, we've got this M1D stencil, which is an iteration of Laplace's equation for diffusion, where we're using a list. Effectively, this is implemented as a shift buffer by the compiler to then be fed into the calculation, and we're averaging the previous, the next value for each point in my domain. So, I mean, this is a very, very quick and basic overview. The language itself has loads and loads of constructs in it that we find useful for porting over HPC kernels, and then our compiler translates this down into Xilinx, C++, HLS for Victus. Really looking at testing two hypotheses. Firstly, is performance portability between von Neumann and data flow architectures possible, or do we need to use a specialized language, specialized abstraction? And secondly, building on such data flow constructs, do we get this fast by construction approach that we think is so important for the technology? So thank you very much for listening, and I'm looking forward to this discussion afterwards.